So there's a lot to learn about projectile motion before we can start really getting into doing problem solving. Now, you need to know that an object experiences a constant gravitational force near the surface of the Earth, and that causes it to undergo uniform acceleration, so a constant acceleration of 9.8 meters per second downwards. Now, I added this in. This doesn't pop up until we get to gravitational forces, but you need to be able to explain that the acceleration of a projectile is always downwards, and it's independent of its mass. So I popped it in a little bit early, but it's applicable to projectiles. You also need to be explained that in the absence of air resistance, the horizontal component of velocity is always constant. This is vital to being able to problem solve. And then you need to be able to analyze multi-image representations of projectile paths. So, first things first, acceleration of a projectile is always downwards. So acceleration is 9.8 meters per second downwards, and it's constant. Okay, the reason why it is constant is that the Earth applies a gravitational force downwards on all objects inside its gravitational field. And this causes objects to be accelerated downwards, because when a force is applied to a mass, it accelerates in the direction of the force, generally, the net force. Now, as I've mentioned, acceleration due to gravity is 9.8 meters per second squared, and usually it's going to be a negative to signify that it's downwards, because it's a vector quantity, acceleration. It's constant, acts throughout the motion of a projectile at all times, so this acceleration vector is the same everywhere. It's always going to be the exact same at all points throughout the object's motion. Even here, when it's stationary at the top of its path, acceleration is still negative 9.8 meters per second. It's just stationary for a split second. Here it's accelerating downwards, here. Always acceleration due to gravity, it's constant throughout its motion. Now, if you look at this diagram, what's happening to the vertical components of velocity? Well, initially we have a large vertical component, but because acceleration due to gravity is acting downwards, it's reducing the vertical component of velocity. So large, it's getting smaller, and at the top of its flight, its vertical component of velocity is actually 0. So it's purely going to have a horizontal component of velocity at the top of its flight. Now what we see is the vertical component of velocity is starting to increase, and then when it strikes the ground, its vertical component of velocity is at its largest. So vertical component of velocity decreasing on its way up to the top of its path, and then increasing on the way back down to Earth or the ground. Now, as I said, we'll talk about the force due to gravity more later on in the course, but basically any mass inside the Earth's gravitational field is going to have a gravitational force applied to it, and this gravitational force is actually directional proportional to the mass of an object. So this elephant, huge 10,000 Newton gravitational force, this tiny little 1 kilo toy is only going to have a small 10 Newton gravitational force. So the force acting on different objects of different masses is larger or smaller, okay? And we'll talk about it on a deeper level later. Now, so this elephant, larger gravitational force. However, because it has a larger mass, basically Newton's second law of motion is that force is equal to mass times acceleration, or the acceleration is directly proportional to the force applied and inversely proportional to the mass of an object. What actually happens is that the acceleration of these two objects is actually constant. It's 9.8, rounded up to 10. So larger net force due to larger mass, but because it has a larger mass, it's actually got more inertia, and inertia is an object's resistance to its change in motion, if you can't remember what inertia is. So inertia is an object's change to resistance in motion. So this elephant has a larger resistance to change in motion, whereas this has a smaller resistance to change in motion. But anyway, what happens is that basically boils down to everything falling or accelerating down to Earth at the exact same rate. So if you drop a coin and a bowling ball, and if air resistance doesn't really impact them, even though the bowling ball might be 10 kilos and the coin might be a few grams, they're going to hit the Earth's surface at the exact same time, because they're both accelerating down to Earth at the exact same time. So it's always downwards, and it's independent of mass. Mass has no bearing on its acceleration downwards. However, in reality, projectiles are affected by air resistance, but we're going to be ignoring the effects of air resistance, or saying that they're basically negligible. Later on we'll look at the effects, but for now, negligible effects. So basically what's going to happen is that there's going to be no forces acting in either direction really, vertical or horizontal, but we're going to focus on the horizontal direction. So there's going to be no forces acting in the horizontal direction, which is why, look at the horizontal component of velocity. At all points in the object's motion, the horizontal component of velocity is the same because there's no forces acting in that direction. And Newton's first law, all the laws are coming in. Newton's first law is that an object in motion will stay in motion at the same speed or will remain in motion at the same velocity unless acted upon by an unbalanced force. And we're assuming there's no unbalanced forces in the horizontal direction because gravity can't be horizontal and we don't have air resistance. So therefore the horizontal component of velocity is constant, which is going to be super useful later for solving problems. Now, here is a multi-image representation. You could be asked to analyze one. They're not a very common exam question anymore at all. But basically what we have here is we have two balls. One ball is launched horizontally. This black ball has double the mass of the white ball. So this black ball is heavier. This white ball lighter. It's only dropped. So the white ball is dropped off the table. This black marble is launched horizontally. Now, what's happened is every split second of time, frame rate, a picture of the ball has been taken and they've been laid one over the top of another. That's a multi-image representation. So each split second. So looking at analyzing this graph, we can come up with some conclusions. Now, what we can conclude is the following. The first one is that the horizontal component of velocity is constant. So at each frame, the ball has moved the exact same amount of space, amount of distance. So the horizontal component of velocity is constant. We can also say that the vertical component of velocity is changing with time. So the ball is actually, if you look carefully, it's always spaced out the same amount and it's dropping the same amount. So the vertical component is changing with time, but this vertical acceleration is completely independent of mass. So if you dropped a marble and you rolled a marble off at the same time, they're actually going to hit the ground at the exact same time because the vertical component is independent of mass. And the time of flight, the time it takes to stay in the air, is completely does not depend on the horizontal component. So the other big conclusion that I've underlined is that the time of flight of a projectile only depends on vertical velocity, which is going to be vital later. So when we use our equations of motion later, we only really care about our vertical component when trying to work out how long something's spent in the air or how long something will take to touch the ground. So time of flight depends only on the vertical component of velocity. Acceleration is independent of mass, and the horizontal component is always constant, never changes, because there's no forces acting against it. So I'll stop that video there.